heat, mass. What else? What do you think power is? If I told you, how do you get more power in a technique, how would you do it?
Put all the muscles in the body together. The more muscles you have, the more power you're going to have.
Well, what do you think it is then? In the scientific philosophy. Velocities in there, do you think? Okay.
Yes. Combining all your muscles together.
Okay, is that you mean in mass? The bigger the person, the more power they might be able to generate. Do you think that's true?
No, sir. I think it's concentrating it also.
Concentrating it also. Interesting. What do you think it is?
Excuse me, it's mass moving, and the only way to get it more power is either get it going faster or get it going longer speed, longer span.
Span meaning time?
No, span means distance.
Distance, okay. What does that mean when somebody does something for a longer distance? You know, you start out a technique here. If you have longer arms than somebody else, you might get your arm up to what? A different, what, at the end, before you strike something? You know,
Speed.
a different speed.
Higher
So speed might have something to do with it. But do you know what the word power means from a scientific viewpoint? A lot of people use scientific terms and they really mean many, many different things from it. A person says you might have political power or you have mental power. But what we're going to describe today is just what the scientific viewpoint is. And I think that we can probably get a lot out of the analysis. I think that you're going to find that a lot of the things that you do, you do well because of the scientific principle behind it. Power, Bellman already knows this because he's a physics engineer person, but power scientifically is work per unit time. If you put more work into it, and that's not necessarily the kind of work that you exerted today, this morning doing karate aerobics. This is a scientific work. But if you put more work into something, and you do it for a shorter amount of time, then you're going to get more power, correct?
Yes, sir.
If you reduce this, you make this very, very, very small, and you keep this the same, that means that you've increased power. Or you can keep the time that you do something the same, and you can do more work over that same time, and you have increased your power. It doesn't matter. That's what it is. However, when you look at a karate strike, it's much more complicated than just power. Because if you look at this piece of plastic here, let me just have it here. If you look at this piece of plastic, the only way that you're going to break it is if you put enough stress on it for a given amount of time to overcome the natural tendency of the thing to stick together. If you can put more stress on it than it's capable of holding, you've broken it. And that's how you break bricks. That's how you break wood. If we want to understand power, therefore, we have to understand what? I think everybody understands time, don't you? I don't have to discuss time. Okay. Is this the towel I used?
Yes, sir.
So what's work? Tell me what work is. What is it?
Energy being expended.
All right. So work equals energy. What else is it? Expended. Any other definition? What's another good definition? Yeah.
Sir, it's amount of force over a distance.
Ah, we have another physics. Unfortunately, science, you see, is valuable and is successful because it doesn't have a lot of different meanings. You don't have shades of meanings when you talk about different terms. It is very, very specific. So that in science, the work is defined as something very, very mundane. It's just force times distance. If, from a scientific viewpoint, I took, whatever this is here, if I did this and I just took this thing from this point and moved it over to here, have I put any force on it? On just this object here? No, because the only force that can exist on taking an object moving an object in space here is to let it drop, and that's called gravitational force. There's a real force there. My muscles had to exert force, of course, to lift it, and so there's an amount of work that I have to expend in lifting this thing up against gravity. But once I'm at a certain height, I can do this, and this object doesn't have any work associated with it. That's pretty restricted, isn't it? That doesn't include all kinds of energy transfer or energy transformations that we might come across. So that what we're going to do today, for just a little brief time anyway, is to look at just this very restricted definition. There has to be a force, and there has to be some distance. If I had I don't know if you've heard of Bruce Lee's one-inch punch. Remember that famous punch? Just like that, and the person goes flying back against the wall. People were always astounded that he was able to put people up against the wall. You know how he did it? Does anyone know how he did that?
Sure.
How?
Put his body behind it using his hips.
What else? How do you think he did? How is he able to stand 1 inch away from somebody like that, and they would end up against the wall? You know how he did it? How?
He spent more work, less time.
Okay, that's efficiency maybe? What?
Focusing power.
Focusing? You know how he really did it?
Yes, sir.
How?
Energy transfer.
Energy transfer. There was one other subtle method that he used that no one ever saw. When he punched somebody, why don't you hop up here? I'm not going to flatten you against the wall, but what he did was this. He came in here. He rose up right underneath the solar plexus here. And he put so much pain into the individual that the only way that they were going to release that pain was to fly backwards out of the way. He had a lot of energy. You're going like this, and the person's going to go up against that wall just to get away from it. Because you can create a lot of pain in there. So he put a lot of force, obviously. But there was a little bit of subtlety going on, too, that the individual just didn't want to withstand anything going in that powerful into a solar plexus. Like this. That's how they did it. 1 inch. These knuckles right in here. So, what we need to describe is force. What's force? See, the problem with trying to understand something, you open up a whole can of worms. We're talking about power, that's the name of the talk. But to know power, you have to understand work, or energy. To understand work, you have to understand what force is. So what's force? Yeah?
Mass times acceleration squared.
No, not square, but we'll give you the mass times acceleration. Someone mentioned speed in here, and of course acceleration is very associated with speed. So it's mass times acceleration. That's what force means. That means that if you have a larger mass and you keep the acceleration the same, that you're going to increase your force. You can have a smaller mass and move it quicker, and you can also increase your force. A lot of times we emphasize over and over again that to get the most efficient use out of your body, you have to relax your muscles. You cannot accelerate as efficiently a tense muscle as you can a relaxed muscle. Here and then out again. At the end of the technique, 80%, toward the end anyway, you tighten everything up. So you're right out there. But to accelerate, it's much more efficient to relax. And that's very, very difficult for people to learn because they feel that they can get more power if they're all tense and tight and hard. And it's just not true. So let's go ahead and look at how we can get a little bit better acceleration, how we can put more mass in there. How can we put more mass into a technique? What is that called? Yeah.
Sir, combining your muscles.
Combining?
Combining groups of muscles.
Okay. What else? What would be another good method?
Locking in.
Locking in? What?
Body motion hips.
Concentrating your striking point, too.
Concentrating? Okay.
So that you're, instead of a fist...
But that's not going to change force, though. I'm talking about how you would increase your force just before you make contact with something. And concentrating, of course, has more to do with when you actually hit the target. That's ki, okay. That's not gonna, is that gonna increase your force?
Yeah.
That's more concentration, isn't it? And release and the snap that comes out after a contact is made.
Good stance.
Good stance, okay. That's also after you make contact with something. If you aren't in a good stance, then you're going to absorb a lot of things back. Which brings us to what famous principle? What famous principle says something, and when you make contact, when you put a force on something, something's going to happen to you. What is that?
It's for a reaction of the equal opposite.
Oh. Do you realize that I would say 80 or 90% of all sport activities depend upon that fact? You know that, did any of you see the Olympics this year?
Yes,
Sir. You know, I don't know if they did this, but you know the sprinters in their starters blocks? Do you ever see a sprinter that pops right up at the very beginning and runs?
No,
sir. I don't know if you've ever done any sprinting, but that's a no-no. If you watch a world-class sprinter, they're right down here. So everything is as linear as possible so that they can maximize the acceleration in the direction that they're traveling. They don't want to accelerate up because that's not going to win them a 100-yard dash very easily. What they want to do is maximize that. And they're putting a tremendous force on him in the nose, up in here, or him not doing anything. Okay, I gave him a choice of, do you want your nose punched or do you want your nose not punched? What would you choose? But do you realize that if I take my fist here and I punch him in the nose, that force, there's a reaction force created in his nose that's equal and opposite to my force. They're both the same. They're both the same force. All right, my force comes in here, into his nose, and there's an equal and opposite force on my poor fist. Why do you think? Why do you think that he would choose to not have his nose punched if there's an equal force coming back into my fist? And that's what Newton's law says. For every action, this is an action, there's an equal and opposite reaction.
Oh, God.
Shoot. Well, the reason why is because even though the forces are equal, the effect of the force is different, unfortunately, right?
Yes, sir.
Your nose is broken, and I have a hurt hand, and there's so much force put into your nose and so much force that your nose put into my hand. They're both equal. But the effect of the force on your nose is vastly different than it is on my hand. My hand can absorb that force back into it, whereas your nose can't. Thank you. So that's one thing that we all should understand, that action-reaction principle, and that has a little bit. What kind of energy do we have in nature? What kind of energy can we tap to make our technique stronger? Let's hear some ideas. There's lots of energy sources out there.
Breathing.
But that's not an energy source. What's an energy source that makes a technique stronger? Yeah.
Sir, adrenaline?
Adrenaline? In what way? How does adrenaline make a technique stronger, faster, or give more energy to a technique?
Sir, if you're prepared to do something and to do it right, finish it correctly with the most force, the most power that you can.
Okay, adrenaline is what would you call adrenaline? What kind of a substance is adrenaline? What?
Sir, a chemical?
A chemical. You've heard of chemical energy, haven't you? There's a whole industry. It's now probably has a bad name because of India, but there is a chemical industry out there. That's a very powerful force, energy source, because we do what with our bodies to get energy? Wait, what is it? What kind of sources, want everyone to start thinking here, what kind of sources do we utilize that we can tap into to get the energy that we need to do a good strike? Yeah. Food. Okay, food. Those are chemicals too. They go into our body, correct? Where does food come from? Okay, be more specific.
Ground of the sun.
Vegetables. How do those are all what? What foods are grown, correct? What gives energy to the food to grow?
The sun.
Okay, solar energy. Without it, you couldn't grow food, right? You couldn't digest that food to get energy, the chemical energy, in order to make a strike strong. So we're all the way back to the sun. What kind of energy does the sun exert? How does it power itself? How does the sun power itself? Fusion. Have any of you heard of fusion or nuclear type reactions that go on in the sun? So we're now down to the subatomic level. That's how come we can get a good punch. It's because atoms in the sun are doing their thing to give energy so that plants can grow, and that we can use those plants, we can harvest them, and we can digest them, and then that turns on a whole very complex chemical reaction system, in which in turn does what? Let's focus in on the chemical reaction systems in the body. How do we power something? How do we get power out of our muscles? What's the main energy there? Main motion?
Contraction.
What?
Contraction.
Contraction. Remember that. A muscle, when it contracts, and it's burning fuel to do so, because if there was no fuel in there to burn, it wouldn't be able to contract. And that's how come we can go from this position here, where you contract your bicep, and you stretch your triceps and the back muscles up in here, and then you could punch out. Does that make sense to everyone?
Yes, sir.
Does everyone realize how complex this study is? And that I can't cover everything in 20 more minutes? Right? So I'm not going to. Okay. Let's now look at, we have a lot of different energy sources. When I hit something, and we haven't talked about really hitting anything, what makes something break? If you go in and punch through a piece of paper, you have to exert a little bit of energy. If you go and punch a 1-inch piece of 12 by 12 pine, you have to exert a certain amount of energy. If you go in and you want to break through a brick, you have to exert a certain amount of energy. If you go in and you want to punch a 1-inch piece of oak, good luck. Good luck. Why do you think demonstrations rely so heavily on time? And why do they put them all together, not as one solid piece, but as one set of individual pieces? No more than, say, 1 inch thick, generally the 3/4 inches. Why do you think that's true? Because there is a limit to how much energy you can probably expend to go through something. Obviously, you can't punch through steel very well, and most people don't try it. So that if you can only expend a certain amount of energy, you want to do it in a flashy way, you do it on something that you can break. And there's a limit. If you have a 1-inch piece of pine, you could do it. But if you have a 1.5-inch piece of pine, it's going to get extremely difficult. And 2 or 3 inches would be almost impossible for anyone to do. Unless you took a down lineman or something and ran their heads or something into it. That'd be about the only way you can do it. So, how do you break something? Quick.
Stress.
What's stress? Is that what happens when you don't do your karate aerobics? Probably. And you have Master Brock up. Well, that's stress.
When you do it.
That's what happens when, you can't win with stress because it's always around us, right? If you do it right, you stress, and if you do it wrong, you find out and you stress then. So what is stress from a scientific point of view? I hate to, narrow these things down, but when something is so broad and has so many definitions, we can't focus in on it and get much information from it. So we're going to focus in on stress from a scientific viewpoint. What is it? Does anyone know? What do you think stress is? If I put stress on that Makawara, is that a Makawara plane? Camper. Who's going to win? I'm going to get the stress right back on me. There's not going to be much stress put on the rope there. What is stress? What do you think stress is? You think that, does it sound reasonable to you that if I put enough stress on an object it might break? Does that statement seem reasonable to you? If I said to you, if I put enough energy into an object, it might break, yeah, that says almost the same thing. But stress has a connotation that's a little bit deeper. Because now you're putting something under stress, isn't that right? If I stress a brick to the point where it busts, that's what's going to happen. That's what nature tells us. Oh, if any of you do breaking, you'll always come up with, in demonstrations, a piece of wood that will not break. I've seen that happen. It's happened to me. You know, I mean, you're trying to do something, say a front snap kick or whatever, and it just doesn't break. You know, so you smash it or something like that, and it still doesn't break. And you throw it against the wall, and still, you know, there's always something that defies logic. You know, that's life. But what is stress? If I put stress onto a piece of wood, what's happening? Yeah. Okay, stress and pressure are equivalent. They're the same thing. So what's pressure?
When you're trying to force something out of its natural position, out of its natural state.
No. Well, in a sense, you're right. In a sense, you're right. Do any of you ever use air in a garage and fill up your tire? Well, you're putting molecules into the tire, right? That's called pressure, right? You have a certain, 30 pounds per square inch. That's pretty typical for a tire, I think. So you're putting lots of molecules in there. You're heating them up. They're hitting the sides of the tire, or the rubber in there, and that's what inflates the tire and keeps it inflated. That's how come when it's cool, those molecules aren't moving around so much. They kind of condense down and huddle around because they're all cold, and the thing deflates. But stress is different. Those are molecules. That's gas we're talking about when we talk about pressure. Stress we put on material objects, like pieces of wood, like bricks, like a slab of steel. You put stress on a material object. And so that's a very important distinction. But what is stress? What's the definition of it? Yeah?
I'll take a stab at it. Does it have anything to do with resistance?
No?
Amount of resistance that your fibers in a piece of wood, whatever amount of resistance it takes to separate them, would that be...
Well, yeah, you're right in that sense. Yeah, sure. The object itself has resistance to whatever energy you put into it, and if you put more energy in than it can resist, in your sense, then that's what happens when you break it. Well, let me just give you the definition of it. It's very important for you to remember some of these concepts. Stress equals the force that you put on something divided by the area. Force per unit area. Why do we tell people to punch with these first two knuckles? Why not punch with the whole hand? Well, because we're putting the same amount of force. Remember, the force doesn't have anything to do with how we strike an object. The force has to do with how relaxed we are in our muscles here, over how much distance we can accelerate our technique, and at the very point just before we make contact, we'll have a certain amount of force. To be efficient with it, we want to increase and maximize this quantity as much as we possibly can. And so we can do that two ways. Here we go. We have a division in here. If we have the same force, we could do what? To make this increase. Do what?
Apply to a smaller area.
Aha! We can reduce the surface area. You know, student A and student B, they have about the same equal size punches and their arms weigh about the same. Okay, so they'll have the same forces. But if one puts it in a smaller area, concentrates it in a smaller area, that means that you're going to put more stress on the piece of wood. And I'll guarantee you that student A, who's doing that, is probably going to break the wood, and student B is just going to have a hurt hand. Maybe wound pride and all that too. So if you have the same force, you reduce the surface area. Or you can increase the force here and have a larger area, correct? Or the same area, say. Well, what's easier to do? Isn't it easier to have as fast and good a force as you can, maximize this, and reduce this as much as possible, and still have a good, strong technique so that you can maximize this quantity stress? And that's what we do in karate. We're told to strike with the ball of the foot. We aren't told to strike with the whole sole of the foot, are we? Are you? When you were first taught front snap kick, for instance, you know, strike with the ball of the foot. When you're taught to kick back kick, what striking surface do you use on a back kick? The heel. Why not the whole bottom part of the foot? Yeah, larger area. Not efficient. Because that means that you have to move your big leg muscles that much faster to have more force if you're going to be very inefficient with the way that you actually strike an object. So that's what stress is. Is there any question about what work is, about what stress is, and about how we tap into our energy sources? Any question on those fairly basic quantities? Nuclear, molecular, all kinds of those energy sources. But what are the two main types of energy that you have? I know you already know it, so I'm not going to ask you. Yeah?
Positive and negative.
Positive and negative, okay? Is there any other? No, I'm not going to ask you either. Non-trains here. What? I've already talked to you. Yes, Mr. Baker. Electrical. That's a type of energy. That's a type of it. What I'm talking about is a more broad definition that electrical and nuclear could all fit under. Yeah.
Potential and kinetic.
You want physics?
Electronics.
Let's write those down. Kinetic. What is kinetic energy? What's the definition for? Someone says kinetic energy. What do you mean?
Stored potential.
No, that's potential energy. What's kinetic energy? What's the implication? Motion, right? Motion. Okay, kinetic equals motion. Potential means what? Static. What's another? Static. Static refers to time. Stationary. What does that mean? Well, if this is motion, what would potential energy be? So what would that be? But now we're going to start cooking here in about 3 minutes. All right. Do you mind if I write things all over this board here? All right. Kinetic energy is energy of motion. Does anybody besides this guy down over here, you're like the student's pet, you know, always raises their hand and has the apple and stuff. You have the apple. I'm not going to ask you any more questions. Does anyone know what a good definition of kinetic energy is? We should all know this, even though we aren't physics people. Because if a white belt comes up and says, well, how do I get more energy, kinetic energy out of my technique? You know, you don't want to say, well, you know, you better be placed better, or you better be more stationary. You know, we don't want to say those things. We want to be able to tell them how to do it, all right? So what is it? What's the definition of kinetic energy? Somebody? Just start spitting it out and we'll finally get it. I'll guarantee you. Say something. What? No, that's we call circular argument. You're going right back to saying exactly what I asked. What is the definition of kinetic energy? What does it include? If we can get to two things that it includes, then I'll be pacified and I won't jump all over you. What is it?
Mass.
Mass. Okay, that's quick. We got one. Speed. Let's do that. Velocity. Speed and velocity will say the same. Even though we know, some of us, that it's not. I don't want to confuse anybody. All right. What I'm going to do is I'm going to say this. It's equal to 1/2, isn't this awful? Mass times velocity squared. Now, you can ask Mr. Dennis in his AAU exploits whether he thinks that speed is important in sparring in championship matches. Do you think it is? Did any watch the poor Super Bowl? The Super Bowl that was supposed to be so great and was such a pathetic mess? Well, you look at a running back, they don't weigh much, do they? Well, relative. Let's talk about relative terms. They weigh more than all of us put together, right? But just relative. A running back doesn't weigh too much compared to a down lineman, who weighs about 3 times as much as the poor running back does usually. Isn't that true? I mean, if you had a running back that weighed 300 pounds, do you think that he'd be traveling very fast? No. I mean, he wouldn't even find himself up into a hole. I mean, he wouldn't know where holes existed in a line, because they would close up a couple centuries before he'd ever get there. Okay, so you have a little guy, not, little, geez, he weighs 225 pounds, but you have a little guy, who gets moving, who's small enough so that he can accelerate fast enough to get into the hole, and then he's off and running if he can get through the linebacker. Well, have you ever seen a little guy against a 300-pound tackle or, 250-pound linebacker who actually takes the linebacker back, because of his motion? Yeah, it's the same thing. In tournament sparring, if you're fast, it doesn't matter if you aren't real big. You don't have to have a lot of mass to create a lot of power because of this nice little term here, which is a squared term. And I'm not going to go into the mathematics of squaring numbers, but if you have a certain energy at one speed and you double your speed and do nothing else,